Hello, this is Tuesday's lecture for week 14. As you know, we're only going to do 3 sections in chapter 5. The first one is sequences, and then we're going to talk about induction and recursion. And I think this is maybe the most mathematically complex of the things that we've talked about so far. And perhaps you're familiar with the summation and pi notation, but if not, then this will be new to you. So I just wanted to go over some of the points from the chapter in more detail with you. So the first section goes over sequences and how we write our sequences in this explicit form. And as an example, to identify the sequence terms from an explicit formula, and this isn't the way it's written in your text, but you're familiar with this notation now, that this is the formula for a sub k, the kth element in the sequence, for all positive integers k. And so if you want to find out what a sub 1 is, for example, you just substitute 1 for k, so I'd have 1 over 1 plus 1 is 1/2, and then let's say we want the third, the a sub 3, or the third element in the sequence. I substitute 3 for k, so now I get 3 over 3 plus 1, or 3/4. So finding, I think you will agree that finding any element from an explicit formula is pretty easy. But going the other way around, when you have, you're given a series of terms and you have to find an explicit formula for the series, that's not so easy. That you have to really kind of engage your cleverness for this, right? And there's a couple tricks. One of the first ones I'd like, in fact, maybe the only one, well, there's a different one down here that I'll talk about, but this alternating sign trick, if you're not familiar with it, we're just going to use the fact that -1 to any even power is positive and -1 to any odd power is negative. And so if you want to alternate the signs for every term in the series like this is, you just use -1 to the k or -1 to the k plus 1, depending on whether it's the even terms or the odd terms that are negative. In this case, the even terms are negative, so I have to take -1 to the k plus 1. So this is, you just throw this in there every time you need alternating signs, and you'll see this in the Taylor series expansion for sine, for example. Sine or cosine functions have alternating signs. And then I find it sometimes useful to say, okay, this is the k equals 1 term, this is the k equals 2 term, and then this kind of leaps out to me. I see, oh, for k equals 2, it's 4, for k equals 3, it's 9, and then I can see that I can, what's the word? I can see the trend, or I can see where this is going, right? All I'm doing is squaring the denominator, and so I can express the answer as this alternating sign trick over k squared. Okay, and this is the summation notation. This funny symbol is a capital sigma, so capital Greek letter sigma, or S for summation, as opposed to the pi, which you're going to see later, so capital P, basically, in the Greek capital pi for product. So summation is expressed like this. We have our dummy variable, so we're going to replace k with integers between m and n, where m is the lower limit and n is the upper limit. So you just write it as a series with a bunch of addition signs in between. And then particularly beneficial for computer scientists is this recursive definition of the summation symbol. And you start with this thing, which seems like a duh, everybody knows that, right? For k equals m to m, there's only one term in this series, and I substitute m for k and I get a sub m. So that's almost obvious, I think. But then we're going to use the fact that we know what the summation is for a single term, and say if we have the summation from n to n, then I can always peel off the last term. I can say it's the summation of all of this except for the last term. So m equals m to n minus 1, and then here's the last term, k equals n to n. And we know from this definition that the sum of k equals n to n of a sub k is just a sub n. So this is the way you'll see it expressed in your textbook, is that the series is equal to the previous sum, a sub n, or I should say, sorry, the previous sum from m equals n to n minus 1 plus the last term. And so you can just keep going backwards until you get the whole series. Okay, this is one of the things I find to be the most difficult, and I'll tell you what really confused me when I was starting, and that is, I make it sound like I've been doing this forever, but no, it's true. You look at this, and it wasn't really explained to me, and so I thought, oh, this is simple. All you do to find a formula, if you're given that this is the series of numbers, and they tell you what the last term in the series is, then that's essentially giving me the formula for the series. They called it n instead of k, but why can't I just write this? Um, is it not the sum from k equals, let's say, 1 to n of k plus 1 over 2k? Isn't that it? And the answer is no, it's not it, because this is not the formula for the nth term. It's the nth term when k is equal to n. And to kind of demonstrate what I mean by that, I wrote, well, maybe I should say more about this. K plus 1 over 2k. Let me just sort of convince you that this is not the formula for this series that we're seeing by writing out the first couple of terms. So for k equals 1, I have 1 plus 1 is 2 over 2 times 1 is 2. So my first term is 1. And my second term, k equals 2, I have 2 plus 1 is 3. And k equals 2, so 2 times 2 is 4. And then my next term is, well, you can kind of see, maybe I don't need to do this. But so I got 1 plus 3/4 instead of 1 over n plus 2 over n plus 1. So this is not the formula, the explicit formula in the summation. So hopefully that dissuades you from the notion that you can just use the last term in the series as the explicit formula in the sum. So I don't know, I'm not really convinced yet. And so let me say this another way. Is there a way to deduce an explicit formula from the last term alone? And the answer is no. So here, the last term is n plus 1 over 2n. So let's think of all the ways that we could, all of the explicit formulas that would satisfy this last term equation when n is equal to k. Well, one way is n plus 1 over n plus k, or another way is to make this n equal k in the numerator, but leave the n in the denominator. Another way is to leave n plus 1 in the denominator and change k equals n in the denominator. And then finally the correct answer is let n equals k in the numerator and let n equals n and n equals k in the denominator to get n plus k. And so there's no way to distinguish between these four formulas just by looking at the last term. Right? They all satisfy this last term for k equals n. But as you can see, I did the expansion for each one, and they're all very different sequences. These are all very different from what the actual sequence is, which is this one. So only this fourth answer gives us the correct first terms of the sequence, even though all of them give us the correct last term in the sequence. And then the other problem with this is, you'll notice here I was a little sneaky. I changed the summation. Instead of from 0 to n, I made it from 1 to n, because I have this problem. At k equals 0, this blows up. So I'm like, well, obviously we can't use k equals 0. But the truth is that this, just looking at the last term, doesn't tell you where the series starts. So that's another reason why you can't deduce an explicit formula from the last term, because you have no idea where it begins. I just arbitrarily chose 0, but I could have just as easily chose 1 or 17. Okay, so all that to say, you can't just use you can't just use the formula for the nth term where n equals k in order to derive an expression, an explicit formula in your summation. It's better, in fact, the only way to do it, in my opinion, is to look at the first terms and see if you can identify the next term in the sequence. I'll be honest with you, I looked at this and I came up with a different solution than the book came up with. I'm like, well, this is the first term, so I'm going to let this be equal to k equals 1. And this is the second term, where k equals 2. And now it looks like I'm adding not k, but 1 less than k. So this is the form that I chose right here. I said, well, maybe it's this, right? Why not? That works. You start at k equals 1 and you plug all that in, you'll get this this sequence. Is it the same? Well, okay, so I was just explaining my method. So my method is to look at the first terms in the sequence and to see if I can identify this progression. And then I'll just write down the formula for the progression. Then the last thing I do is I check it for k equals the last term in the sequence. Well, the last term in the sequence is, to be honest, I checked k equals n. I thought, well, maybe we end with k equals n, and then I got the wrong answer. So I realized it's got to be k equals 1 to n plus 1. So now let's check this for the last term in the sequence. When k equals n plus 1, I have n plus 1 in the numerator. Check. When k equals n plus 1, I have n plus n minus 1, which is 2n. So that's equal to the denominator in the last term, so that works out. All right, so I came up with a completely different formula than your book has for this sequence. Are they the same? Are they equivalent? And the answer is yes. And the way to tell they're equivalent is to do a change of variables, and this is discussed later on in the section, but I wanted to show you the way I do change of variables, which I think is much easier than the way EP explains it. So let's say I want, instead of going to n plus 1, I want to end with some variable n or j or whatever. Who cares, right? So I'm going to make this substitution. I'm going to let j equal k minus 1. So if I do that, now I just look at this. Now I can solve this for k. Right? If I add 1 to both sides, I get k equals j plus 1. So that's just solving this for k. And in green is my original formula. K equals 1 to n plus 1. Remember that this is the upper limit, where k is equal to n plus 1. Well, instead of k, now I'm using j plus 1. So I stick an n plus 1, j plus 1 in every time there was a k. Now I get j plus 1 equals n plus 1. And if I subtract 1 from both sides, I get j equals n. So that's my upper limit. And then the lower limit was k equal 1. But now, because of our substitution, we're letting k equals j plus 1. So instead of k, I have j plus 1 equals 1. I solve this for j. I get j equals 0. So this is my lower limit, j equals 0. Upper limit, j equals n. And using k equals j plus 1 and just making the substitutions, you get this, which is the expression that you'll see in the F book. So there is no unique formula, and you can switch from one form to another just by doing this, by changing the dummy variable. They call it a dummy variable because it doesn't matter what it is. You could change it back now. Instead of calling it j, you know what? I'm going to call it k. So I'm going to say this is the same thing as k equals 0 to n of k plus 1 over n plus k. Like, that's no fair. You're using, look, you changed this into this. Those look like different formulas, but they're not, right? Because once you do this expansion, your k variable completely disappears. So it doesn't matter what symbol. You can use q or elephants for this, right? They're all going to disappear when you write the expansion. Maybe that's why they call it the dummy variable. All right, and EP also discusses a recursive. Oh, I already talked about it. Okay, sorry. Let's use the recursive form of the summation to simplify some expressions. One is, let's say we want to look at the sum going from 1 to n plus 1 of 1 over I squared. Well, using our recursion relation, that I can rewrite this as the series from 1 to n plus whatever the last term is. And the last term would be where I is equal to n plus 1. So it's 1 over I squared, n plus 1 squared gives me this as my last term. This is the sum from I equals n plus 1 to n plus 1 of 1 over I squared, right? So the other thing that I wanted to mention is I put in brackets, put this in brackets in red, and it's not needed, but I just wanted to emphasize that whenever you see a summation, it's like an implicit grouping symbol. So if you don't need these brackets, but make sure you understand that it's not the same as this. Wow. Don't write so well with this thing. Right, it's not the same. If you want to say that, then you have to use the brackets. So think of the summation like parentheses in the PEMDAS order of operations. Okay, and let's look at this the same problem backwards. Here we've kind of peeled off this last term. The last term is 2 to the n plus 1, and rewriting this in this form. Where's my recursion thing? Oh, right here. Right, this k equals m to m of a to k. Writing it in this form, I get that it's the summation from n equals from n plus 1 to n plus 1 of 2 to the k. Well, then I realized that here I have the same explicit formula in the summation, but one goes from 0 to n and the other goes from n plus 1 to n plus 1. So I can put that in one big series from 0 to n plus 1 of 2 to the k. All right, now here's another thing that EP explains in a cheating way, I think. And I say cheating because she starts out by giving you this identity that 1 over k times k plus 1 is equal to 1 over k minus 1 over k plus 1. And then you can do this trick of breaking the summation apart into two separate summations, same limits, but different explicit formula. This is one of the theorems, 5.1.1 theorem, right? That you can break a sum of a sum or difference into a sum of summations, a sum or difference of summations. So this is good to know. We can do the same thing with the pi notation. But how do you come up with this the start place how do you come up with this to begin with? And the answer is partial fractions expansion. And just perhaps you've already had partial fractions expansion in your algebra class, but I don't think it would hurt to revisit that. For example, if somebody gave you this problem and said, go ahead and simplify this sum, unless you knew partial fractions expansion, you wouldn't know how to do it. Right? You don't have this memorized, that 1 over k, at least I hope you don't, that 1 over k times k plus 1 is equal to 1 over k minus 1 over k plus 1. And the answer is you can figure this out pretty quickly just using algebra, right? We know that if we're going to assume that it can be written in this form. There's some fancy rules if you have more than one factor of k or k plus 1 in the numerator, but just ignoring that for now. We know that we expect that we should be able to write this fraction with product in the denominator as a sum of fractions with each product in the denominator. Well, in order for that to be true, when I add these two together, they have to have the same denominator. To give this term the same denominator as that term means I have to multiply the top and bottom by k plus 1. If I multiply the top and bottom of this by k plus 1, and I multiply the top and bottom of this by k, then they'll both have the same denominator, k times k plus 1, and so then I have this expression. And if I distribute my k's and then collect like terms in k, I just get k times a plus b plus a, and there is no k on the right hand side, right? So whatever the coefficient of k is has to equal 0. And then I just have a 1 for my constant term, so this a has to be equal to 1. And when I make the substitution, 1 plus b equals 0, I solve that for b, I get b equals minus 1. So that means, so now I've done my partial fractions expansion of this, and now I can break this apart like this. Expansion from of 1 over k from 1 to n looks like that, and the expansion from 1 over n to 1 over k plus 1 looks like this. So you'll notice all the terms are the same except for the first one and the last one. That means they all cancel except for the first and last term, and so you can just write the total answer like that. And then the next thing EP talks about is product notation. So we're going to use the capital pi, think P for product, and that's just instead of having a bunch of plus signs between all your terms, now you've got a multiplication symbol between all your terms, or the convention, as you know in algebra, is just to put the terms next to each other when you mean multiply. And then here's the recursive form of what we looked at for the summation notation previously. It's just, you can take the last term, a to the n, and multiply it by all the previous terms. That's the way to solve this recursively. And EP also doesn't write this in the book, and I suspect the reason is because it's not super clean because of this k equals n term. But in my mind, the biggest reason for introducing this product notation is to talk about factorials, because probably you've already run into this, but we use factorials all the time in math and physics. And the reason is, I mean, it's a shorthand way to express this pi notation from k equals 1 to n k, right? So it's just equal to k times k minus 1 times k minus 2 times k minus 3, etc., until you get to 1. And we stop before we get to k equals 0 because anything times 0 is 0. So we have this this difficulty to deal with. One is that if you did the factorial of 1, just the number 1 factorial, well, that's equal to 1. Oh, we're done, right? Because there is no other term. I go from k equals 1 to n. But if you have 0 factorial, there is no k equals 0 term. So what do we do with this? Well, we just are going to let it equal to 1. We're going to say, by definition, or by convention if you prefer, it's equal to 1. And this allows, this has to be this way because it allows us to write binomial expansions in a really cool and clean way, and it fits with this n choose r business that we'll talk about in a second. All right, and then here's another thing to be careful with is order of operations again for factorial. Do you remember seeing factorial symbol in your PEMDAS? Remember, PEMDAS was please excuse my dear Aunt Sally, parentheses, exponents, multiplication and division, addition and subtraction. Where's factorial in there? Well, it's not really in there. I would say it's on equal footing with the exponentials, and it's definitely before multiplication. So when you see n times the product, well, n times n minus 1 factorial, that doesn't mean n times n minus, it doesn't mean this. It means first you do the factorial and then you do the multiplication. So it's ahead of multiplication and division in the order of operations. And then I say it's on equal footing with exponentiation because it's usually pretty obvious by context. For example, here I'm sure you understand that you do the exponentiation before you do take the factorial, but here you take the factorial before you do the exponentiation. So it just depends on whether or not it's in the whether it's a superscript or not. Okay, let me do these examples. Here we're going to use the recursion formula again to calculate what n plus 1 factorial over n is. Well, I know that n plus 1 factorial is equal to n factorial times this last term, n plus 1. And now I see that I can cancel the n factorials in the numerator and denominator. So this is just equal to n plus 1. And similarly for this bottom one, I have n factorial in the numerator, which is equal, try that again. Let me start out with writing out the factorial for n factorial. That's n times n minus 1 times n minus 2 times n minus 3 times n minus 4, etc. Well, instead of writing all the rest of that out, I'm just going to say that's n minus 3 factorial. And now I see that it'll cancel with the n minus 3 factorial in the denominator. So then I can just FOIL that out to get n squared minus 3n plus 2 times n. Alright, this is not going to help you with your homework, but it's an extremely cool thing to know. And this is the n choose r. Actually, I think she does ask you corrections. She does ask you some n choose r questions, but she doesn't put it in this context of the binomial expansion. I don't know if you've run into this already in your algebra class, the fact that n choose r is a way to figure out what the coefficients are of any binomial expansion term. But let me start that let me introduce the topic by talking about the definition of n choose r. It means how many ways can you choose r things from a set of n things. So for example, if you have 6 people, Larry, Mo, Joe, Bob, Larry, Mary, Joe, Bob, Mo, and Curly, and I want to know how many couples are possible. So how many ways can I choose 2 people from this set of 6 people? And I know there's only one female name in here. Don't let that trouble you. We're not going to concern ourselves with sexual preference here, but I just want to know how many people can Larry pair up with. Um, he can pair up with Mary, or Joe, or Bob, or Mo, or Curly. So 1, 2, 3, 4, 5 different things. Larry has 5 different people he could pair with. And now let's do the same thing for Mary. Mary, well, I don't want to count Larry because I already have the Larry-Mary combination. So I'll just do Mary and Joe, Mary and Bob, Mary and Mo, Mary and Curly. So Mary has 4 possibilities. She really has 5, but we've already counted Larry and Mary, so I don't want to double count that. And now if I do the same thing with Bob, we'll see that he has 3. Mo will have 2. And Curly, sorry, did I say 2? Mary has 1, 2, 3, 4. Joe has 1, 2, 3. I forgot Joe. Poor Joe. Okay. So that means Mo has 2 and Curly has... No, I forgot Bob now. Jeez, this is terrible. Bob has 2, Mo and Curly, and Mo has 1. He can just be with Curly. And now Curly, poor Curly, it seems like I'm saying there are 0 possibilities of pairing with Curly, but that's not true. We've already counted all of the possible pairings of Curly with all the other players. So that means we have 0 additional couple options with Curly. So if I add these all up, I get 5 plus 4 plus 3 plus 2 plus 1. See, 9 plus 3 is 12, 14, 15. So 15 different pairing combinations. Alright, well that wasn't too bad when I had, how many ways can I choose a set of 2 people from a set of 6 people. But imagine when the numbers get bigger. If I'm looking at number of ways to choose 3 people, it gets, forget about doing it this way, right? To do them by hand, it gets prohibitive. It turns out that there's a simple formula, not that simple, but here's the formula for figuring out how to do it. Like, how does that, this is a summation, here we got factorials, how can that possibly be the same? Well, let's look at it. Here I've got a set of 6 people, and I want to choose 2 things from that set of 6. How many ways can I choose 2 things in the set of 6? And the answer is 6 factorial. Well, here it is. It turns out to be 15, right? Oh, here I use the recursion trick again. 6 factorial is 6 times 5 times 4 factorial, which cancels out with the 4 factorial in the denominator. And then you could, if you want to get really fancy, you can cancel this 2 with this, so it's just 3 times 5. Alright, so we got the same answer. Oh no, that's not a proof, but hopefully it'll convince you that it's the same. So one of the reasons why this is so important mathematically is that it happens to be, we have this, if you aren't familiar with Pascal's triangle, please Google Pascal's triangle and just spend 20 minutes going down that rabbit hole. You won't regret it. It's a pretty amazing thing from number theory. And this is kind of a generator for Pascal's triangle. Anyway, so if you want to find do this expansion of a plus b to the n, right? It could be some binomial to the 17th power. Now we have a formula for finding out what any of those the coefficients are. For example, if I want to find the coefficient of the x squared term in the expansion of x plus 3 cubed, if I did it the normal way, I should say the kind of laborious way, well, I start out by foiling this, x squared plus 6x plus 9, and then to get x plus 3 cubed, I take x plus 3 times that product, and I have to add like terms. It's a mess, right? But you get this. So let's do it with the binomial theorem instead, just using the how many ways can you choose one thing from a group of 3 things, and that turns out it's pretty easy. It's just 3, and so then I have to multiply it by my b sub k, and remember k is equal to 1 in this case, so 3 to the first power is 3, 3 times 3 is 9. Okay, so you get the same thing. So it seems like, well, maybe that's a little bit easier, not much easier. But let's just look, this isn't really that much bigger, but if you have x plus 3 to the 7th power, good luck doing the x plus 3 to the 7th power longhand with algebra. It's very laborious and time consuming. In fact, if you can do it in less than 2 hours, I'll give you a Twinkie or something. I mean, it'd be impressive and really boring mathematical feat. Instead, let's use the binomial expansion to figure out what the x to the 4th coefficient is. You could also write this out in Pascal's triangle pretty quickly. And we say, oh, maybe this is worth pointing out. I want the x to the 4th term. Well, the exponent is n minus k. That means I want n minus k to be equal 4. If n minus k is equal to 4 and n equals 7, that means k equals 3. So I write the choose 3 out of 7 binomial expansion term, and I get this 35 times 27. So yeah, you don't have any binomial expansion stuff on the homework, but I just wanted to make sure that you were exposed to that at least once in your life. And if you have any questions at all about the homework, please don't hesitate to text or email me. Take care.